Hey, this is Elite with Simpson Math, and in this video, we're going to be talking about how to use Desmos to answer normal probability questions. So let's get started by taking a look at this example. We're going to be talking about IQ scores in this video. IQ scores are normally distributed with a mean of 100, standard deviation of 15. Reminder that the shorthand looks like this, and Desmos will produce a version kind of thing of this. We'll have, instead of just in, it'll say normal dist, mean of 100, standard deviation of 15. We're going to let X represent the IQ score of a randomly selected person. So the first one I want to know is, let's say that your IQ score is 110. What's the probability that we get a randomly selected person to be less than 110? So one note that I have less than here. I think Desmos uses less than or equal to. When it's a continuous distribution, it doesn't really matter. It's the same thing. Just a note about my sketch over here. My students, I encourage them to, before they go to technology, draw a picture of what they think the problem is asking, so that way they can compare their interpretation of the problem to what the picture Desmos produces. And also, especially really helpful for less than, greater than, things like that, just to make sure that they don't get lost in the sauce doing the calculator work, that they end up like they can kind of like make kind of a quick guess. So without even me thinking about this work here, I can look at this and go, oh, well, this should be more than 50, less than 80-ish or so. So less than 84, actually using the empirical rule. So you can kind of make a judgment call there. 70, 75%. Turns out that actually is pretty close to 75%. Let's go ahead and hop over to Desmos. There's, like is, actually, before I do that, just a reminder, there are two general ways. You could find the z-score, and then find the area less than that particular z, or you could just jump in doing it in context. We're going to do it in context first, and then I'll backtrack and show you about the z. So here on Desmos, there's two general ways you can get it. There's the newest way, and it's nice. I'm going to show you that one first. With your cursor in some empty line, I'm going to click on this plus in the top left corner to add an item. I'm going to pick inference. Now, we're not doing statistical inference right now. If you're in a stat class, that'll come later. But this does have a picture of a normal distribution, which is nice, and that's the one that we're going to be using. So pick inference, and one of our options within inference is the probability distribution. Let's select that. Don't do anything with inference right now. Like I said, in a stat class, that'll come later if you're in a stat class. We have a probability distribution. You can pick your probability distribution. We're doing normal, so we'll just stick with the default. These top four above the line are continuous. These bottom three are discrete. You might get to those later. Notice it's gray. We have a gray 0 and a gray 1. Desmos, throughout their platform, whenever you see a gray value, that is the default value. So if you don't do anything, it will input those values. I'm going to go ahead and input a mean of 100 and a standard deviation of 15. You can just type those in. I have a real keyboard on my computer, so that's why the on-screen keyboard isn't coming up. Just typed it in and click or press enter. It will go ahead and zoom in a bit to the normal curve here. You saw it kind of like aggressively zoomed down. For some reason it didn't, or you moved it, or you hit the home and it's kind of zoomed in weird. You should be able to see this zoom fit button. So it's on the same line as the input one that you had. You should see a little magnifying glass with a plus in it. Click on the zoom fit. It'll zoom us out to our question, to our distribution here. There's some helper text. It's telling us that the first input, the first parameter is a mean, comma, the second thing is the standard deviation. So that's just letting us know what it did. Let's toggle open the cumulative probability. Cumulative is because it's accumulating. It's that cumulative probability. A reminder that the area under the curve adds up to 100. So if I put in like negative 900 to positive 900, actually I can just delete them. Desmos lets me just have infinities. So if I have, oh, it's defaulting to those. I want, fine, negative 99 to negative a whole bunch to positive infinity. Notice that adds up to 1. So the area under the curve adds up to 1. We're wanting to find the area under that, which then will also translate to that probability. So I'm going to find the area less than 110. So notice we have inner, outer, left, and right. So this left one matches my picture a little bit better, because I want to find the area less than, so we're doing the area to the left. And then notice it's defaulting to 100. It's nothing special, it's just defaulting to the value in the mean, just so that we have something to answer, so that way when you click through inner, outer, left, and right, it you know what you're doing. It's you're not, it's showing you, it's trying to represent what's happening. So I don't want to find the area less than 100. I want to find the area less than 110. So I'm just going to key in 110. Notice it was automatically updating when I did 1. It was a really small number, a little bit less small, but 110 is then our number. So here it's rounding to 3 decimal places for us. If for some reason you're needing more than 3 decimal places, more than 74.8% or 0.748, you can click anywhere, but it does show this little down arrow signifying that there's something that's going to happen if you click on it. And it pops open a whole lot more decimal places. If you just want to write down the answer from there, so be it. If you want to do something with this, you could click on this box and it will kind of copy and paste it, export it out, so that way you could maybe give this a value, or copy paste it, or do some math with it. If you wanted to cut this in half or something, you could easily just divide it by 2 like that. So you can click on this and hit the export to be able to do something with that number pretty quickly. All right, so that's the area less than a number. I did talk about how I wanted to show you how you could do use a z-score instead. So let me show you the other way. So like I said, we could do plus, inference, probability distribution, do my mean of 0, standard deviation 1. I could do that. When I do, I'm going to change this color so it's blue. We could do that. Notice I didn't put any values. I just left it at 0 and 1. And so it doesn't put anything here, but it is telling us in gray here the Desmos is defaulting to 0 and 1 and just leaving it empty like that. So if I wanted to find the area less than a z-score of 2/3 or 0.6667, we can do the same thing. Less than 2/3, 0.6667, or a little bit better, just go ahead and put in the 2/3. And notice we do get the same answer, like the exact same answer. That's because those have the same area, even though they're physically, different graphs. They're just scaled differently, but they are representing the same amount of area. I did say that there were 2 ways that you could get this, so let me show you how we could get that again. You can open up to the side of my face right here. We have the on-screen keyboard. You can click on that to open up the on-screen keyboard. Then we want to do functions. Scroll a bit, past stats, past list operations and visualizations, and we want to do the probability distributions. Just pick just pick normal dist. Make sure your cursor is in an empty line, normal dist. And this is what we saw a second ago. It defaults to mean of 0, standard deviation 1. If I wanted to do the 100, 10, 100, 15, I just do 100, 15, and then zoom fit. Or I could leave it blank and do the z-score. So you don't have to go through the interface thing. I like to, because it just, I like filling in boxes. All right. All right, so we've done that question. Let's see what's next. So now I'm going to find the area greater than 110. Let's find the area greater than 110. So over here on my, over here, I can just switch this to the right. So I have a 110 in here. So if I do the area to the right of 110, that's the area greater than 110, I now get 0.252. And we should notice that if I put this back to left and export this number out, if I do 1 minus the answer we had previously, the answer we had in part A, I get this 0.25249 and so forth. If I switch this to right, look at this number. It's the same number as that, because they're literally complements of each other. The area to the left is the complement of the area to the right. So if I want to find the area greater than 110, then it's just 1 minus what we found previously, or just do the area to the right. Again, showing you that there is no thickness here. Desmos does show an equal to, which is fine, because whether it's greater than or equal to, it's mathematically the same thing, because this is a continuous distribution. So that's what we do: less than, and then greater than. And then if we wanted to do a between, so between 80 and 110, let's say your IQ is 110, your buddies is 80, you want to find that the percentage of people between you, or the probability of selecting a random person, between the two of you, so we could do an inner situation. So notice if I did, this is about to be wrong. I have 110 on the far end on the left and then 80 on the upper. Whoa! Actually, I hadn't tested this. It corrected it for us. It didn't break. So I'm going to do 80 to 110. I was a little surprised because what it just did was look at the less thans. When they're less thans, we should have small to big, but I have it big to small, and so it kindly flipped around the inequalities for us. How about that? Uh, let's not do that. No, I like to go ahead and it to be 80 to 110 because that makes more sense in my math brain. So 80 to 110, 80 is less than x, which is less than 110. So we can get the area between those two, and I get 0.656. If I wanted more decimal places, I can toggle up the thing to get more decimal places. All right, a few before we do the inverse process, let's talk about the absolute value. So mathy people like to work in absolute value sometime because they're weird. So let me toggle this closed and um, let me open up functions, scroll down and pick normal dist. Zoom in on this. Let me just work on this green one. So I'm going to leave it at mean of 0, standard deviation 1. I'm going to go ahead and put in 0 and 1 just so that way it's clear that that's z-score. So the problem that we're being tasked to find, first let's do the area. The probability that we get a z, the absolute value of z, is less than 1. So let's talk about that. Let's test a few numbers. So let's test 0. So if I plug in 0 here, do I get a true statement? Well, what's absolute value of 0? 0. Is 0 less than 1? Yes. So 0 is happy. What about if I put in a 2? So if I plug in a 2 here, I know that looks like a z, but if I put in a 2, and the absolute value of 2 is 2. Is 2 less than 1? Nope. So we don't have anything over here on this side. What about a negative 2? Absolute value of negative 2 is a positive 2. Is 2 less than 1? Nope. So negative 2 doesn't work. So I could plug in any number between almost negative 1 and almost 1, and I will get a true statement here. So we're actually going to be between negative 1 and 1. So knowing that, we can come here, toggle open my cumulative probability, leave it at the inner. Actually, it is right here, between negative 1 and 1. From our empirical rule, we know that that's about 68%, or my 689599.7, we know that's about 68%. Turns out a little bit more accurately, it's closer to about 68.3%. All right. Then what about if I wanted to find the area? The question was the probability that we get z is greater than 1. The absolute value of z, rather, is greater than 1. We can test our points again, but this time when we test 0, it won't work. But when we test the 2's, the 2 and negative 2, it does work. This is actually the complement of that. So we could take what we did before and just do 1 minus. So I could export out this number and do 1 minus it, put my cursor to the front, do 1 minus. And so we should get 0.3173. Or we could just do outer. The outer of, so this, when I switch it to outer, it's taking this negative 1 here, going less than negative 1, and greater than my positive 1, greater than this bigger number. So less than negative 1 or greater than 1 is then that outer area. All right. Now let's switch gears and do an inverse process. So this says, we're going to find the boundaries of the following regions. This says the highest IQ among the lowest 20% of IQ scores. This hurts our brain a little bit because this says highest IQ among the lowest. So that saying is, if this is the lowest 20%, the highest, the cutoff point, because there is no cutoff point this way. Well, I guess an IQ of 0, I don't think we can have negative IQ. In theory, this goes to negative infinity. So, but the cutoff point would be the highest point on the low end. So we're looking for this number. So in terms of drawing my picture, I have a normal curve, and my mean of 100, standard deviation 15. This time I know what the shaded region is. It's 20% and it's on the low end. I don't know this number and I want to know it. I should know that this tick mark would be 85, 100 minus the 15. So I know that this is 85 and this is a bit to the right of that 85. I don't think it quite makes it to 90. So it's, something a little bit bigger than 85. Well, how are we going to end up doing that? The mathy way is to do a little bit of math and solve for that x once you get this corresponding z-score. Well, the full way is to just switch our bounds around. So let me show you the more direct way, and then we could backtrack with our z's. All right. So I'm pressing this big circle to turn off the z and turning on the distribution. All right. So I'm going to find, I have a left than shaded thing, but this time I want to compute the bounds. I want to compute the boundary. I know my area. I don't know the bounds. I'm wanting to compute the bounds. Let's click the bounds to switch. You can also know which is which, because notice what's changing when I'm toggling between these two. When I click on area, my input is a boundary and my output is the area. You can tell the output is there because it's the thing you could click on to get the full answer or the more decimal places. If you do bounds, my input is now what was my output before, and my output is now this x value. All right, so I want this left region to be 20%. 20% as a decimal is 0.2, so I'm going to have 0.2 here. And that feels about right based upon my shading that I drew a second ago. And I get 87.38, which feels pretty good. Earlier I said it should be a little bit bigger than 85. Look, it's a little bit bigger than 85. That makes me feel pretty confident about my answer. That's why it's a good idea to give a quick sketch before you kind of move on. But again, if I want more decimal places, toggle open the little pop-up. We can get a lot more decimal places there. The way to do it more mathy, let me put this math back up, would be to figure out what the corresponding z-score would be. So if I had to figure out what the z-score that would be at negative, that would be at the lowest 20%, the upper boundary of the lowest 20%, I should get negative 0.84, and then I could solve. So over here on my normal distribution, let me do the same thing. I want a left. I want to be my regions to the left. I want to be computing the bounds. I'm going to be putting in 0.2. And when I do, notice I get a negative 0.84, actually negative 0.842-ish. So when I do the math for this, I put in that for my z. I don't know my x. My x is my unknown. I do know my mean and standard deviation. They're 115. And then we just do a bit of solving. Multiply both sides times 15. And then add the 100 over. And that's why this might come in handy. I'm going to export this out. Go ahead and do the multiply by 15. And then add the 100. And then I can go ahead in one swoop, do that algebra and get the 8737, which notice is this number right here. So what Desmos rather is doing in the background, I'm presuming here that it's basically doing this, and it's doing these two things together for you because you have this the input of the mean and standard deviation. All right, let's quickly go through the other questions. Oops. All right, so if I want to find the lowest IQ among the highest 20%, so if someone is bragging that they're in the upper 20% of IQ scores, you would be like, okay, well, what's the cutoff? Well, I want to be in that club. What's the lowest IQ that I need to be able to be in that club? Well, it's basically the same thing we just did. Instead of a less than, it's going to be to the right. Let me get rid of the picture. It's going to be to the right. So just switch everything over to the right. Notice we have a 112.6, or it's a positive version, this positive 0.84, or that positive 0.842 times 15 plus 100 gives us that 112. And then what's the lowest and highest IQ scores bounding the middle 40% of IQ scores? So if I want to find the middle 40%, let's work through this one. I'm going to get rid of the Z one because I don't want it right now. So if I want the middle 40, so my work says it should be about 107 to 92. From our quick sketch, we should know that it's definitely going to be within one standard deviation, well within that one standard deviation, because it's less than 68. So I'm going to switch to inner. And again, I'm going to leave it at bounds. This inner and outer, I believe, only works with the middle. So we can just leave it at this bounds and change this to 0.4. This is a lot nicer than they used to be. Before you would have to do the middle percent dance a little bit and can think about what would be on the outside here. So we would if you're not using Desmos, you need to think, well, the entire area under the curve is 100. If here in the middle is 40, that leaves me 60 total on both, collectively on both sides. Just one of them is 30. So that's how you would be able to have to go about that way by putting in the 30. But here we can just say inner, the middle 40%. So this has to be the middle 40 because there's really an infinite number of 40% we could have in the center of the graph-ish. Like if I scooch this to the right a bunch, I could scooch this to the right a bunch as well, and I could find some a 40% thing. It won't be the same width. That's why it's a whole mess. So this is always the middle. And then when I do, I just put in this 0.4 for the middle. Sorry, 0.4 is my shaded area in the middle, and I get what I got earlier, the 107 point. I had 0.8 and 0.13. I might have been doing something a little bit more rounding. I bet this will be a bit more accurate. All right, lastly, what about the IQ scores? So if this is the, what are the IQ scores? Sorry, what is the IQR for IQ scores? So just a reminder that the IQR is the width of the middle 50% of the data. So you could go about finding Q1 and finding Q3, which we'll do that in just a second just to verify, or you can just put in middle 50%. So if I change this to 0.5 in the middle, I get these two numbers. I get my upper bound, which is this 110, minus, let me see if it will go in if I do that. No, it won't. But I could cut and paste. There you go. So my 110 minus the 89-ish gives me this 20.234. This is the Q3 minus this Q1 gives me that 20-ish. So my IQR is this 20-ish. Again, what did I do? This is the middle 50%, which is the width in the middle 50% is the IQR. So I took those two bounds and subtracted them. Let's be a little bit more mechanical about this. Reminder that the IQR is the middle 50%. It's also Q3 minus Q1. So let's just find the area to the left. And let's say that I want the area to the left of the lowest 75%. This would be Q3. So this shaded region 75%. This is Q3. This 110.11734 yada yada. This is Q3. Then I'm going to find Q1, which is the cutoff for the 25th percentile. So if this is the lowest 25th percent, do we get 89.88, 89.88, so forth? So this is Q1. So when I do Q3 minus Q1, we get this 20.23. But notice, again, I want the middle 50%. So the middle 50% these are the cutoffs for the middle 50%. The distance between them is the IQR, or the middle 50%. And there you go. That's the IQR of IQ scores is about 20, a little bit more than 20. All right. I hope this helped you understand the normal distribution using Desmos a little bit easier. It's pretty nice because it shows you what its output is by being this little box, shows you this input by being what's on the blank line. Once you understand how to go about getting it set up, it's pretty self-explanatory, nice interface. All right, hope this helps. I'll see you in the next one. Bye.